When we look back at the massive tectonic shifts in how human beings conduct business, we almost always picture physical things.
Oh, absolutely. The big industrial milestones.
Right, exactly. We picture the assembly line stamping out Model T Fords, or we picture the steam engine.
Yeah, or transitioning from literal horse-drawn carriages to a fleet of motorized delivery trucks.
Yes, the milestones of progress have historically been things you could, literally reach out and touch.
They were tangible.
But today, any manager or executive trying to run an enterprise is standing right in the middle of a shift that is, well, entirely invisible.
Invisible, but incredibly loud.
Yeah, and infinitely more powerful than the steam engine. I mean, imagine a corporate landscape where absolutely everything is online.
And we aren't just talking about laptops here.
No, not at all. We're talking about the smartphones, the printers in the hallway, the security cameras over the doors.
HVAC systems.
Yeah.
The company cars in the parking lot.
Right, everything. It is a completely hyper-connected world. And, it's a massive double-edged sword.
It really is.
Because on one hand, you have global reach, right? Instantaneous data flowing from every single corner of your operation.
That sounds great on paper.
It does. But on the other hand, you have managers and operations teams that are practically drowning in information overload.
The expectation is just 24/7 availability.
And the noise is absolutely deafening. So the core question we have to tackle for you today is this. How does a corporate manager or an IT leader turn this chaotic web of constant data into a streamlined competitive advantage?
And that is really the defining question for modern management right there.
Because we have the connections, right?
Right. We've built an infrastructure that connects everything, but, well, connection alone does not equal efficiency.
Definitely not.
Unmanaged connection, especially in a corporate setting, usually just equals total operational paralysis.
Yeah, we just assume that because data can travel instantly from, a warehouse in Shenzhen to a boardroom in Chicago, the business is somehow inherently better.
Exactly. But if the boardroom doesn't know how to filter or process and actually act on that data, the speed is actually a huge liability.
Which brings us to the mission for this session. This is Chapter 1 out of a 15-part deep dive series we are calling Telecommunications for Managers.
And today's focus is the evolution of communication technologies.
Right. And before we jump into that baseline, if you are an IT leader or a manager, take a second to like, subscribe, and share this deep dive.
Highly recommend it.
Yeah, subscribing ensures you always maintain a competitive edge in this hyper-connected marketplace. And explicitly, make sure you check the description for access to additional corporate resources, diagrams, and technical reading that pair perfectly with today's analysis.
There's some really great material in there.
Definitely. So, to set the competitive baseline for this entire series, we are going to explore how legacy systems transition to modern networks.
And how a deep understanding of these networking principles really bridges the gap between academic theory and high-level corporate decision-making.
Because we have to move way beyond just knowing the acronyms, right?
For sure. We need to look at how this infrastructure actually drives the business forward.
So, to do that, let's establish the reality of the environment modern businesses are operating in.
The hyper-connected world.
Right. That phrase, hyperconnectivity, it gets thrown around a lot in tech circles, but we really need to define the actual mechanism of what that means for a workforce today.
Yeah, because historically, connecting to a network was, it was an intentional stationary act.
You got to try to do it.
Exactly. You walked into an office, you sat down at a physical desktop computer, you listened to the dial-up modem scream at you.
Oh, man, that sound.
Right. You logged on and you did your work. But when you walked away from the desk, you were disconnected.
You were unreachable.
Yes. But today, hyperconnectivity means that devices are persistently tied to digital networks.
They never drop off.
Right, allowing for remote transactions and personal and business activities without any intentional logon action from the user.
Basically, if it has a power source, it has a network address.
That's a good way to look at it. And the advantages are, they're obvious.
Oh, yeah. Very few transactions require a physical presence anymore.
Right. You can authorize a multi-million-dollar supply chain purchase while sitting in an airport terminal.
But the psychological and operational blowback of that is severe.
It really is. The primary drawback is information overload.
Because there's this ingrained expectation that everyone is online, connected, and available at all times.
Which means people are constantly checking smartphones, struggling to, actually put the device down.
Yeah, finding it genuinely difficult to focus on deep, unbroken analytical work. or even just face-to-face strategic conversation.
Exactly.
I read that in the source material, and initially I thought, okay, well, this is just a personal productivity issue, right? Like, just put your phone away at dinner.
Sure, that's the knee-jerk reaction.
Oh, but reading deeper, this isn't just about personal screen time. This is a massive structural challenge to daily business operations.
It acts as a critical operational bottleneck.
Because human beings have a finite amount of cognitive bandwidth.
We do. When you're a manager and you receive, say, 500 emails, 200 instant messages, and 50 automated alerts from various dashboards in a single Tuesday.
Which is pretty standard, honestly.
It is. The sheer volume of that data actively slows down your administrative actions.
The decision-making process just grinds to a halt.
Exactly, because the manager is spending 80% of their energy just triaging the noise to find the actual signal.
I keep picturing the modern corporation as a living organism.
Okay, I like that.
Right. And we've given this organism an incredibly sensitive nervous system.
It feels everything.
Yes. It has sensors on its skin, in its eyes, all over its body, and it can feel every single stimulus instantly.
But we haven't evolved the brain.
Exactly. We haven't given it a brain capable of filtering out the noise. So if a light breeze blows, the organism panics because it feels everything at maximum intensity.
We're letting the connectivity manage us.
Right. Are we managing it, or is it managing us?
That nervous system analogy works perfectly because it highlights the mechanical flaw in how a lot of companies operate today.
How so?
Well, right now, for a lot of organizations, the network acts as just a passive conduit.
Just a dumb pipe.
Right. It just blasts every sensory input directly to the managerial brain without any sorting mechanism at all.
So what's the mandate for IT leaders then?
The mandate is to design infrastructure that doesn't just connect devices, but strategically filters and shapes that flow of information.
So engineering the brain.
Yes. You have to engineer the brain to tell the nerve endings, look, only alert me if the temperature goes above a certain threshold. Otherwise, handle it yourself.
But if we want to engineer that brain, we have to really understand the evolution of the nervous system itself.
Right, where it came from.
Because we didn't just wake up one morning with a fully formed, hyper-connected digital network. We have the ghosts of legacy systems still haunting our modern infrastructure.
Oh, we definitely do. And those ghosts dictate a lot of the limitations and the design choices network engineers face today.
Right, so we have to look at the physical evolution from legacy analog systems to modern digital networks, specifically Internet Protocol or IP networks.
Let's start with the legacy side, the analog world.
Okay, when we say something is an analog device, what is the actual mechanism making it different from a digital computer?
Well, analog devices transmit data using continuously variable signals.
Continuously variable.
Right. The easiest way to visualize this is a wave in the ocean, or the physical sound wave of a human voice.
Okay.
The electrical signal rises and falls in a continuous, unbroken curve.
It's like a classic legacy telephone system.
Exactly. When you speak into an old analog handset, a continuous electrical current is modified or modulated to perfectly mimic the rise and fall of the sound waves coming out of your mouth.
And then that continuous wave travels down a copper wire to the receiver.
Yes. But digital networks operate on a fundamentally different mechanism.
They don't use continuous waves at all, right?
Yeah. No, not at all. They chop data down into discrete individual chunks.
Packet.
Right, we call them packets. And those packets are represented strictly by binary ones and zeros.
And the interesting reality for you as a corporate manager is that the world isn't cleanly divided.
No, it's very messy.
Right, we didn't just throw all the analog equipment into a landfill on January 1st, 2000.
I mean, a modern corporate network is very often a hybrid.
Oh, totally. You might have an old analog phone on a receptionist's desk or, a legacy fax machine in the legal department.
Right, and those connect to an older private branch exchange or PBX system.
And that legacy device is still spitting out continuously variable analog waves.
Yes, it is. But to talk to the rest of the world, that signal has to hit a gateway.
Let's isolate the gateway for a second because that's crucial. How does it actually perform that translation?
Okay, so the gateway basically acts as an analog to digital converter.
Right.
It samples that continuous wave thousands of times a second.
Just constantly checking it.
Exactly. It looks at the height of the wave at each tiny fraction of a second, assigns a numerical value to that height, and packages those numbers into digital packets.
And then those discrete packets of ones and zeros can be fired across the internet or the corporate backbone.
Yep. And on the other end, if the receiving device is also analog, Another gateway takes those numbers and recreates the continuous wave.
It's just a constant process of chopping up the wave and gluing it back together.
That's a great way to picture it.
But once that data is chopped into digital packets, it really enters a new domain.
It does.
And in the digital networking domain, the undisputed king of the road is the Internet Protocol, or IP.
Absolutely. IP is the fundamental set of rules governing how these digital packets are addressed and routed across network boundaries.
The mechanism is super similar to the Postal Service, right?
Exactly like the Postal Service. Every single device on an IP network requires a unique address to communicate, just like every physical house needs a mailing address to receive a letter.
Right. If a packet doesn't have a destination IP address and a source IP address, the routers have no idea what to do with it.
And they just drop it. It's gone.
Which brings up the sheer logistics of handing out millions of addresses.
Oh, it used to be a nightmare.
Right. Because nobody wants to pull out their smartphone, connect to the office Wi-Fi, and manually type in a 12-digit IP address just to check their email.
But historically, that manual entry was the reality.
Wow. Really?
Yeah. In the early days of corporate networking, network administrators literally walked from cubicle to cubicle with a clipboard.
Just a physical clipboard or a massive spreadsheet?
Yes. Manually configuring a static IP address for every single desktop computer.
So if you moved a computer to a different floor,
the administrator had to manually change the address so it matched the new local network.
That is incredibly labor-intensive.
It was an administrative nightmare. But the solution to that was DHCP, which stands for Dynamic Host Configuration Protocol.
So how does DHCP automate that clipboard process?
The mechanism is essentially an automated negotiation.
Okay.
When a new device, say your smartphone, joins a network, it sends out a broadcast message.
Like it's shouting into the void.
Exactly. It's basically shouting, "Hello, I am new to this network. I don't have an address. Can someone help me?"
And the server hears it.
Great. The local DHCP server is programmed to listen for those shouts. It hears the request, looks at a pool of available IP addresses it manages, and automatically offers one to your smartphone.
So it just hands it over permanently?
No, actually, the server leases that address to your phone for a specific period of time.
Ah, a lease.
Yeah. When you leave the building and your phone disconnects, the lease expires, and that IP address goes back into the pool.
To be handed out to the next person who walks in the door.
Exactly. DHCP is really the hidden mechanism that makes plug-and-play enterprise mobility possible today.
But the pool of addresses a DHCP server can hand out isn't infinite.
No, it is not.
Which leads us to the Great Migration. The elephant in the room regarding networking infrastructure.
You're talking about IPv4 versus IPv6.
Exactly. Every IT leader has heard these terms. But we really need to break down the scale and the mechanism of this shift.
We have to look at the math here.
Okay, let's do the math.
So Internet Protocol version 4, or IPv4, was the foundational standard for decades. An IPv4 address is a 32-bit number.
And to a human, that usually looks like 4 numbers separated by periods, right?
Right, something like 192.168.1.254.
Okay.
Because the architecture relies on 32 bits, the absolute mathematical limit for unique addresses is approximately 4.3 billion.
Now, in the 1980s, when the internet was mostly just universities and military research labs, 4.3 billion addresses must have seemed like giving every person on Earth their own private continent.
Oh, it was considered an unimaginably vast number.
But then the hyperconnected world materialized.
Right. We put computers on desks, then we put them in pockets.
And then cars, refrigerators, light bulbs.
Exactly. We burned through 4.3 billion addresses with terrifying speed.
When did we actually run out?
The central authority that manages global IP allocation officially ran out of new, unallocated IPv4 address blocks back in 2011.
2011. So the industry had to engineer larger systems.
Yes, IPv6.
And IPv6 fundamentally changes the addressing math.
It does. Instead of 32-bit numbers, IPv6 uses 128-bit numbers.
Which visually looks entirely different.
Oh, completely. It's a long string of hexadecimal characters separated by colons.
Okay.
And by expanding the length of the address from 32 to 128 bits, the capacity didn't just double. The expansion is exponential.
How exponential are we talking?
IPv6 provides unique addresses for approximately 340 undecillion devices.
Undecillion. For anyone not familiar with that prefix, that is the number 340 followed by 36 zeros.
The scale is almost beyond human comprehension.
It's absurd.
The standard analogy is that you could assign a unique IPv6 address to every single atom on the surface of the Earth.
Wow.
And you would still have enough addresses left over to do the exact same thing for 100 other planets.
That's wild. But beyond just having an endless supply of addresses, does IPv6 actually change how the network routes data?
It does. It creates significant structural efficiencies.
Because of the size of the address space.
Yes, because the space is so massive, network engineers can allocate addresses in a much more organized, hierarchical way.
Okay, how does that work?
IPv6 makes it much easier to aggregate subnets using routing prefixes.
What does that mean for the router?
It means a global internet router doesn't have to memorize millions of fragmented random routes. It can look at the prefix of an IPv6 address and instantly know, everything starting with this sequence goes to North America.
And then the next router down the line says, everything with this sequence goes to this specific corporate campus.
Exactly. It vastly streamlines global traffic because it's geographically and structurally organized.
But what about internal corporate networks?
That's a good question.
Because a lot of companies don't want their internal security cameras or, employee laptops to have a globally routable public address that anyone on the internet can see.
Right, that is a critical security architecture concept.
In the IPv4 days, we had specific ranges of private addresses, like the 192.168 block, that were unroutable on the public internet. Does IPv6 have that?
It does. IPv6 introduces the equivalent concept called unique local addresses, or ULAs.
Okay, ULAs.
Yeah. If an engineer is designing a highly secure, private internal network, they use specific reserved blocks of IPv6 addresses.
How do you identify those?
These blocks specifically start with the letters F-C or FB.
Got it.
And the internet backbone routers are programmed to instantly drop any packet that tries to enter the public internet with one of those private starting characters.
It ensures internal traffic stays strictly internal.
Exactly. It creates a hard boundary.
I have to challenge the timeline here, though.
Okay, go for it.
You noted that the world officially ran out of new IPv4 addresses in 2011.
Yes.
That is well over a decade ago.
Yeah.
Yet, looking at the reality of corporate infrastructure today, a staggering amount of the world is still running on IPv4.
Oh, absolutely.
If we ran out of gas over 10 years ago, how is the car still driving? Who is dragging their feet on this transition?
Well, the delay is really a fascinating study in technical debt and, honestly, engineering workarounds.
Who's to blame?
The enterprise customers are the ones dragging their feet, largely because overhauling the IP scheme of an entire multinational corporation is incredibly expensive.
And risky, I'd imagine.
Very risky, and it offers very little immediate return on investment to the board of directors.
They don't want to pay for plumbing they can't see.
Exactly. But they've been able to delay this because the engineering community provided two massive lifelines.
Let's explore those lifelines. What is the first mechanism keeping IPv4 alive?
The first is a technology called NAT, or Network Address Translation.
NAT.
Yeah. Think of NAT like a corporate mailroom.
Oh.
A company might have 3,000 employees inside a building, but instead of giving every employee their own public street address, the company just has one public street address.
And all the mail comes to the mailroom.
Right. The mailroom opens the envelope, sees it's for John in accounting, and routes it internally.
And NAT does this with IP packets.
Exactly. A company can hide thousands of internal devices, all using those private, unroutable IP addresses behind a single public IPv4 address at their internet router.
So the router translates the internal address to the external one on the fly.
Yep. NAT single-handedly stretched the lifespan of IPv4 by decades.
And what's the second lifeline?
The second is the concept of a dual IP stack.
Dual stack.
Yes. Modern operating systems like Windows, Mac OS, Linux, iOS, they are essentially bilingual.
So they speak both.
Exactly. The software supports both IPv4 and IPv6 simultaneously.
Which hides the complexity.
It completely hides it from both the software developer and the end user. If you write an application, the underlying operating system will dynamically figure out whether to send the packets via IPv4 or IPv6, depending on what the local router supports.
So companies look at the sheer cost of moving to IPv6. They see that NAT and dual-stack operating systems are keeping the lights on, and they just decide to kick the can down the road.
That is the textbook definition of technical debt.
Right.
But the takeaway for managers is that relying on IPv4 workarounds is a ticking clock.
Why is time running out now?
Because the global internet, particularly cellular networks and infrastructure in developing nations, is deploying natively on IPv6.
Oh, I see.
As the world transitions, Forcing traffic through NAT gateways and translation layers introduces latency and overhead. IPv4 will just become slower and more expensive to maintain.
So you have to transition eventually.
Planning a systematic transition to IPv6 using those dual-stack environments to ensure backward compatibility is a mandatory future-proofing strategy.
You cannot build the high-speed automated business of tomorrow on the congested plumbing of the 1990s.
Perfectly said.
Let's shift the focus a bit, because having a beautifully engineered IPv6 routed network is completely useless if the human beings using it are still bogged down.
Right, the technology has to serve the people.
Exactly. We need to bridge the gap between the physical network and the actual work people do.
Yeah.
How do we take all this connectivity and use it to solve that initial problem of information overload we talked about?
Well, we have to transition from managing packets to managing people and processes.
Okay.
And this introduces the discipline of business process management, or BPM.
BPM.
Right. A business process is simply a series of defined steps designed to produce a specific product or service.
So BPM is managing that.
BPM is the formalized methodology of analyzing, improving, and managing those processes. The entire goal of BPM is to strip away the friction.
The source material breaks BPM down into a life cycle with 5 distinct phases: design, modeling, execution, monitoring, and optimizing.
Yep, the 5 phases.
Walk us through how a company actually applies this. Maybe use a concrete example.
Let's use a standard corporate scenario. Employee onboarding.
Oh, everyone's favorite.
Right. When a new hire starts, they need a laptop, software licenses, security badges, and payroll setup.
Lots of moving parts.
Historically, this involves HR emailing, IT emailing facilities forgetting about it, and the employee just sitting at an empty desk for 3 days.
Yeah, that is a broken process.
So, step 1, design.
What happens there?
In the design phase, management maps out the onboarding process exactly as it currently exists. They document every email sent, every form filled out, and identify where the bottlenecks are, like facilities constantly losing the email.
Okay, so seeing the reality. Then step 2 is modeling,
Right. They take that map and they test what-if scenarios.
like trying out a new system.
Exactly. What if HR inputs the new hire data into a centralized portal, and that portal automatically triggers work orders to IT and facilities simultaneously? They model how that changes the timeline.
Step 3, execution.
Execution is actually deploying the new process, building the portal, training the staff, rolling it out to the company.
And step 4 is monitoring, which I assume is critical.
Oh, it's vital. The organization tracks the new process in real time. Are new hires actually getting their laptops on day 1? Where are the new delays happening?
Because there's always a new delay.
Always. And finally, step 5 is optimizing. Management takes the data gathered during monitoring and refines the process.
Maybe realizing they need to add a step for the security team to review building access.
Exactly. And then the cycle starts all over again at design. It's a continuous loop.
And the connection back to our nervous system analogy is that a highly optimized BPM strategy actively minimizes the information users receive.
Yes. In a hyperconnected world, the mark of a good process is silence.
Silence, I love that.
A worker should only receive the exact piece of information they need right at the moment they need it to perform their specific task, and absolutely nothing more.
So the facilities manager doesn't need to see the new hire's salary requirements.
No, they only need a notification that says, "Print badge for John Doe." To achieve this level of surgical information delivery, BPM relies heavily on a technological framework called Unified Communications, or UC.
Let's break down unified communications. What does that actually mean?
Unified communications is the practice of bringing disparate communication technologies, so voice, video, text, presence, email, document sharing together into a single cohesive platform.
It's about removing the friction of switching between tools.
Exactly.
The text highlights a major distinction within UC that managers have to understand. It's the difference between store and forward methods and real-time methods.
Right. These are crucial categories.
Because these serve fundamentally different business functions and put completely different stresses on the network.
They really do. Store and forward communication means the delivery of the message does not depend on the recipient being present or available at the moment it is sent.
Yep.
The message is transmitted, it's stored on a server somewhere, and the recipient retrieves it when they are ready.
Email is the quintessential example of this.
Oh, exactly. You send an email at 2 a.m., it sits on the Exchange server, and your colleague reads it at 8 a.m. Traditional snail mail and text messaging also fall into this category.
And real-time communication is the opposite.
Right. Real-time requires both parties to be present and actively engaged simultaneously.
Like a voice telephone call?
Yes, or a live video conference. Even collaborative document editing, where you can see someone else's cursor typing a sentence at the exact same moment you're reading it.
Right, you're both there.
And a crucial component of real-time UC is presence.
Presence.
Yeah, that simple visual indicator, usually a green, yellow, or red dot next to a person's name in the corporate directory showing whether they are available, busy, or away.
The source material brings up a concept here that I found really interesting, the idea of verification.
Yes, verification is huge.
Because whether you're using store and forward or real-time, the communication isn't actually reliable unless it is verified.
Right. If a process requires a sender to constantly manually follow up, like, hey, did you get my email? Or did that file go through? The process is broken.
It creates massive administrative delay.
Exactly. Reliable communication requires built-in verification that the recipient received the message. In UC, this can be automated.
Like read receipt.
Read receipts, system acknowledgments, or a workflow dashboard that automatically changes status to received the very moment the document is opened.
But a skeptic looking at unified communications might say, you are just giving my employees more ways to be distracted. Now, instead of just email, they have chat pop-ups, video rings, and shared workspaces constantly pinging them.
I hear that complaint a lot.
Right. So how does UC actually reduce the information overload?
The mechanism is context and presence. A poorly implemented tool is just another noise generator.
Sure.
But a tightly integrated UC platform drastically reduces duplicate and meaningless messages.
Yeah. So
Imagine you need an urgent approval from the CFO. Without UC, you might email them. 10 minutes later, you panic and call their desk phone. Then you text their mobile.
you've just created 3 redundant messages, adding to the overload.
Exactly. But with the UC platform, you look at the CFO's presence indicator. It shows a red dot and says, in a client presentation.
You instantly know not to call.
Right. You know the email is the right method, and the system might even allow you to flag the document so it pops up the moment their status changes to green. The friction of finding someone is just eliminated.
But enabling that real-time magic, the video calls, the instant presence updates, requires some serious heavy lifting from the physical IP network.
Oh, absolutely.
Because treating all digital packets equally just doesn't work for real-time traffic.
This is a vital technical reality for any IT manager. Real-time communication is incredibly fragile.
Fragile in what way?
Well, if you are downloading a PDF and the network gets congested, causing a packet to be delayed by half a second, you will never notice.
The file just takes an extra half second to download.
Exactly. But if you are on a live video call and a packet containing the audio of your voice is delayed by half a second, the receiving computer plays the audio out of order.
And the voice becomes garbled, robotic, and just incomprehensible.
Yes. This variation in the delay of received packets is called packet jitter.
So how does the network solve packet jitter?
The network must implement quality of service, or QoS.
QoS?
QoS is a traffic prioritization mechanism. Think of the network as a busy highway. Without QoS, every car, whether it's a family going on vacation or an ambulance with its sirens on, has to wait in the exact same traffic jam.
That's a great analogy.
When a network engineer configures QoS, they program the routers to inspect the header of every IP packet. The router acts like a traffic cop.
Okay.
It sees a packet tagged as real-time voice or video, and it puts it in a dedicated express lane. The router basically says, this voice packet skips the line, that email packet can wait a few milliseconds.
So without strict QoS policies, enterprise video and voice over IP simply will not function reliably.
Will fall apart.
Let's bring this down to a really practical managerial decision. Imagine a CTO for a large hospital network.
Okay.
She is overhauling the communication infrastructure. She knows she needs a UC platform. When it comes to selecting a specific tool, say a secure messaging and telehealth video application, should she purchase a standalone application that is hyper-specialized for healthcare? Or should she go with a bundled suite from a massive vendor that integrates all voice, chat, and email natively?
That is the perennial best-of-breed versus integrated suite debate.
Which one wins?
Well, if the CTO chooses the standalone application, she is buying the absolute best feature set available for that specific task. The telehealth video might have specialized integrations for medical imaging or custom diagnostic tools that a generic suite lacks.
That sounds good for the doctors.
It is. However, the operational cost is incredibly high. She has just created an isolated data silo.
Ah, I see.
The presence information in the telehealth app might not sync with the hospital's main email directory. The IT department now has to manage a separate set of user accounts, a separate security perimeter, and a separate vendor contract.
What does the integrated suite offer instead?
Native integration. When a doctor is in a telehealth video consultation, their status automatically changes to Do Not Disturb across the entire hospital directory.
That's powerful.
And the chat logs from the consultation are automatically encrypted and saved to the patient's centralized electronic health record. The IT overhead drops dramatically because there is one vendor, one security policy, and one management dashboard.
But the trade-off is that the video tool within the suite might lack some of those niche, cutting-edge medical features.
Exactly. It might be a little generic.
So what actually drives the decision, then?
The business process drives the decision. IT leaders must map their UC strategy directly to their BPM goals.
Okay, that makes sense.
If the hospital's core competitive advantage relies on those highly specialized diagnostic video features, the standalone tool might be worth the integration nightmare.
Right.
But for the vast majority of enterprise operations, the seamless, friction-free flow of information provided by a tightly integrated suite will remove more bottlenecks and drive significantly more efficiency than a disjointed collection of specialized apps.
And once an enterprise manages to streamline its internal communications, once the nervous system is filtered and the brain is making fast decisions, that efficiency naturally spills outward into how the company interacts with the global market.
It does.
The World Wide Web completely altered the physics of business reach.
Oh, completely. Historically, a brick-and-mortar business was constrained by geography. Your customer base was whoever could physically drive to your storefront.
Right.
The web gave that local storefront a global footprint. It birthed e-commerce, which is the practice of conducting business transactions over the internet.
But from a network engineering perspective, e-commerce is not just a monolithic thing, right?
No, not at all. The way a business sells dictates how the network must be built.
The source outlines 3 primary e-commerce models. Let's break down the mechanics of each, starting with B2C.
B2C stands for business to consumer. This is the classic retail model, providing products or services directly to an end consumer.
Think of buying a jacket from an online retailer.
Exactly. The characteristics of B2C are usually fixed pricing. The price you see on the screen is the price you pay. It features a high volume of individual customers, but relatively low volume per transaction.
The customer buys one jacket, not 10,000.
Right. And crucially, there is virtually zero deep system integration required. The customer uses a standard web browser, accesses the public web server, makes a credit card transaction, and leaves.
The retailer doesn't need to connect directly to the customer's personal banking network.
Exactly. It's very siloed.
Now compare that mechanism to B2B, business to business.
B2B is an entirely different beast. This involves businesses conducting transactions with other businesses, typically within a supply chain.
Give us an example.
Imagine a massive automotive manufacturer buying tons of steel from a supplier. The volume of goods is astronomical. The pricing is rarely fixed. It is negotiated based on contracts, volume, and market fluctuations.
Right.
But the biggest difference is the technical integration. The manufacturer's internal inventory management system will often communicate directly, machine to machine, with the supplier's order fulfillment database.
So the systems are talking directly to each other without a human clicking add to cart.
Exactly. When the autoplant sensors detect steel inventory dropping below a certain threshold, their network automatically generates an encrypted purchase order, sends it over a dedicated, highly secure VPN tunnel to the supplier's network, and triggers the shipping logistics.
Wow.
This requires robust, persistent, and heavily secured network connections that go far beyond standard web traffic.
And then we have the third model, which comes with its own unique set of ethics.
Yeah.
B2G, business to government.
Yeah, B2G describes activities between commercial organizations and public sector agencies.
I imagine the friction there is intense.
The friction in B2G is immense because it is defined by strict regulatory constraints. You don't just negotiate a price over lunch. You have to respond to highly formalized requests for proposal, or RFPs.
Right.
The pricing schedules are rigid and legally binding. But from an IT perspective, the network requirements are brutal.
How so?
Connecting your corporate network to a Department of Defense system or a federal health agency requires massive compliance auditing. The encryption standards, the data logging requirements, and the access controls will dictate your entire infrastructure design.
You are essentially forced to build your network to mirror the government's security posture.
You have to.
Transitioning a traditional business into any of these robust online models doesn't happen overnight.
No, it's a process.
The source material outlines 3 distinct phases of transforming a business model. Let's walk through that journey.
Sure. Phase 1 is essentially just dipping a toe in the water. A traditional business decides it needs an internet presence.
Okay, so what do?
They set up corporate email, they build an information-only website, basically a digital brochure with hours of operation and a phone number.
They are still fundamentally operating as a brick-and-mortar business, though.
Right. They might use the web to research competitors or buy office supplies, but they have no real digital strategy for engaging customers.
They aren't actually conducting transactions over the network yet, so how do they cross the chasm into Phase 2?
Phase 2 is the move into actual e-commerce and enhanced customer service. This is where the website gets a secure shopping cart so consumers can actually purchase goods.
They're actually selling online.
Yes. The company starts actively engaging in social media marketing to drive traffic. Internally, they begin deploying unified communications to handle the influx of digital inquiries.
So the website transitions from a static brochure to a tool that provides value-added features, like order tracking or a customer support knowledge base.
Exactly.
But Phase 2 still sounds a bit disjointed, like pieces are working but not fully together. What is the ultimate goal, Phase 3?
Phase 3 is full e-business with integrated applications.
Full e-business.
This is where the internal network and the external web presence fuse into one cohesive machine.
Okay, what does that look like?
The customer service website is fully integrated with the internal UC platform. If a customer is looking at a product online and gets confused, they click a button and the website instantly initiates a live video or voice call with the sales agent.
Oh, that's slick.
Right. And simultaneously, the network pulls the customer's purchase history from the CRM database and pops it onto the agent's screen before they even say hello.
That's powerful.
It also features secure, automated B2B integrations with the supply chain. Everything, marketing, sales, support, and logistics, is completely linked and automated.
Moving an entire corporation from a basic digital brochure in Phase 1 to a fully integrated automated Phase 3 machine sounds incredibly daunting.
It's a huge undertaking.
Beyond the obvious financial cost of the software, what is the single biggest vulnerability a company faces during that transition?
The catastrophic vulnerability is data security and privacy.
Because you're holding so much more now.
Right. When a company moves into Phase 3, they are no longer just storing a few names and addresses. They are capturing behavioral data from social media, integrating it with real-time geolocation from mobile apps, tracking extensive purchase histories, and managing identity access for B2B partners who have direct pipelines into the corporate database.
You are building a massive, incredibly lucrative repository of sensitive data.
Exactly. If the company's network security architecture is still stuck in Phase 1 relying on basic firewalls and weak passwords, a breach is inevitable.
And a breach at Phase 3 isn't just a PR embarrassment.
Oh, no. The regulatory fines and the complete loss of partner trust can be an extinction-level event for the business.
Which means the overarching managerial takeaway is that e-commerce is not just a marketing initiative. E-commerce dictates the network architecture.
100%.
If you choose a B2B model, you must engineer high-volume, secure system integrations. If you choose B2G, you must engineer rigid security compliance. The business strategy and the IT infrastructure are inextricably linked.
You cannot bolt the network on as an afterthought. It is the foundation.
And as these business models scale globally, generating massive amounts of data from B2B integrations and constant UC streams, a localized server closet down the hall from the CEO's office is no longer going to cut it.
No, the scale demands a different approach.
Right. We have to talk about how the underlying hardware scales to meet this demand. This brings us to the final major concepts: the Internet of Things and cloud computing architectures.
To manage a global Phase 3 enterprise, you need unprecedented scale, and you need relentless automation.
Let's address the automation first through the lens of IoT, the Internet of Things.
Right. We established earlier that hyperconnectivity means everything is online. Estimates show there are exponentially more internet-connected devices than there are human beings on the planet.
But how does that actually impact business operations? I mean, what is the practical value of a connected light bulb?
Well, the real business value of IoT is the elimination of administrative delay.
Okay, tying back to BPM.
Yes, exactly. We discussed BPM earlier. Anytime a business process requires a human being to read an email, interpret a dashboard, make a decision, and click a button, delay is injected into the system.
Because humans are slow.
Humans are very slow. IoT moves those administrative decisions into autonomous programs that require zero human interaction.
Give me a tangible mechanism for how that works in the real world.
Let's use an industrial manufacturing plant. Historically, if a massive printing press was running out of specialized ink, a floor manager had to notice the gauge was low.
They had to physically see it.
Right. They walked back to their desk, filled out a requisition form, emailed it to the purchasing department, purchasing approved it, and then purchasing logged into a supplier's website to order the ink.
That process could take days.
With IoT, the ink reservoir itself has a sensor connected to the network. When the ink drops below 10%, the sensor autonomously generates a secure IP packet, routes it through the corporate firewall, and sends an API request directly to the supplier's B2B e-commerce system. The supplier system automatically processes the order, bills the corporate account, and dispatches the shipment. The entire supply chain moved, money changed hands, and a physical product was shipped, all in milliseconds, without a single human being involved.
That is the ultimate realization of a frictionless business process. But the sheer volume of data generated by millions of these sensors constantly talking to each other across the globe, you cannot process that on physical servers sitting in a basement. You need the cloud.
The cloud is what makes this scale economically feasible. At its most basic definition, cloud computing is the practice of renting someone else's computers, storage, and network infrastructure to run your business applications, rather than buying and maintaining the physical hardware yourself.
But the technological magic trick that makes cloud computing possible is virtualization, right?
Yes.
I want to spend a moment on virtualization because it's the engine of the modern internet. Before virtualization, the corporate data center was just a nightmare of server sprawl, wasn't it?
It was incredibly inefficient. Historically, a rule of thumb was one application, one server.
Okay.
You bought a physical piece of hardware to run your email system. You bought another physical server to run your accounting software. Because you had to plan for peak load, say the end of the financial quarter, you bought incredibly powerful machines.
Right.
But on a random Tuesday, that accounting server might only be using 5% of its processing power. The other 95% of that expensive hardware was just sitting idle, generating heat and consuming electricity.
So how does virtualization solve that? What is the actual mechanism?
Virtualization introduces a layer of software called a hypervisor.
The hypervisor.
The hypervisor sits directly on top of the physical hardware. It takes all the CPU power, the RAM, and the storage, and it carves it up. It allows that single physical server to act as if it were a multiple, separate, completely independent computers.
And these are called virtual machines.
Right. To the accounting software, the virtual machine looks and acts exactly like a physical computer with its own operating system and its own IP address, but it's really just a file running on the hypervisor.
So you can take that email server and that accounting server and run them both as virtual machines on the exact same physical hardware, utilizing almost all of the processing power.
Exactly. And the massive advantage is flexibility. If your e-commerce site suddenly gets hit with a viral marketing campaign and traffic spikes by 1,000%, you don't have to wait 3 weeks to order and install physical RAM in a server rack.
The network administrator just logs into the hypervisor and allocates more virtual CPU and memory to the web server in seconds.
And when the traffic dies down, they scale it back.
So virtualization is how the cloud operates under the hood. But how do businesses actually procure these services? The text defines different cloud service models: PaaS, IaaS, and XaaS. Let's break down what a company is actually renting in each model.
Let's use the analogy of a commercial kitchen.
Oh, I like that.
IaaS stands for Infrastructure as a Service. This is like renting a bare commercial space. The cloud provider gives you the physical building, the power, the water, and the gas hookups. In technical terms, the raw virtual machines, storage, and network connectivity.
But the room is empty.
Right. You, the customer, have to bring in your own ovens, hire the staff, design the menu, and cook the food. You are responsible for installing the operating systems, managing the databases, and keeping the applications secure.
It offers maximum control and flexibility, but requires a highly skilled IT team to manage.
Exactly.
Okay, so IaaS is renting the bare kitchen floor. What is PaaS?
Pay is platform as a service. This model is explicitly designed to support software development. This is like renting a fully equipped commercial kitchen.
Okay.
The provider gives you the building, but they also install the ovens, the prep stations, the refrigerators, and they make sure it passes the health inspection. In technical terms, the provider manages the physical hardware, the hypervisor, the operating systems, and the underlying database structures.
You don't worry about patching servers.
No, you just bring your developers, your chefs, and your recipes, and you start cooking. It drastically accelerates the speed at which a company can build and deploy custom applications.
And the most ubiquitous model, SaaS.
SaaS is software as a service. This is like going to a restaurant to eat. You don't care how the kitchen is built. You don't care who maintains the ovens. You just want the finished meal.
Right.
The provider manages absolutely everything: the infrastructure, the platform, and the application itself. The customer simply logs in through a web browser and consumes the software. Salesforce, Google Workspace, Microsoft 365, these are all SaaS.
You just pay a monthly subscription per user, and the complexity is entirely abstracted away.
Exactly.
And finally, the text mentions this evolving term, SaaS. Anything as a service.
SaaS is the logical conclusion of the cloud model. It extends the subscription concept beyond traditional software applications and into specialized business capabilities.
Give me an example.
You can now subscribe to database as a service, security as a service, or even disaster recovery as a service. A company no longer needs to build a massive secondary data center to back up their files. They just subscribe to a cloud provider who handles the entire replication process over the network.
So those models describe what you are buying. But there's also a critical strategic decision regarding where this infrastructure lives, known as the deployment model. Specifically, the difference between public cloud and private cloud.
The public cloud is fundamentally a multi-tenant environment. The cloud service provider owns massive data centers filled with physical hardware.
Okay.
When you rent a virtual machine on AWS or Microsoft Azure, your virtual machine is sitting on the exact same physical piece of silicon as a virtual machine belonging to a completely different company.
Oh, wow.
The hypervisor keeps the data logically separated and secure, but the physical infrastructure is shared. The advantages are infinite scalability and a purely operational expense model. You pay only for what you use, with zero capital expenditure for hardware.
But I imagine that multi-tenant sharing makes certain security officers very nervous.
For organizations operating in highly regulated spaces, like banking, healthcare, or BT defense contracting, sharing physical servers in a public cloud might violate compliance regulations or simply exceed their risk tolerance. They require absolute control over the physical environment.
Which brings me to a scenario. Let's say a listener is a CTO for a regional bank. She wants to modernize her infrastructure, gain the flexibility of virtualization, but without the massive upfront capital expenses of constantly buying new hardware.
Okay.
The textbook suggests a private cloud. But wait, if she needs a private cloud to maintain total isolation, doesn't that just mean she has to buy a bunch of servers and build her own data center again? How does a private cloud solve the capital expense problem?
That is a very common point of confusion. The defining characteristic of a private cloud is not who owns the physical building. The defining characteristic is exclusivity and control over the virtualization layer.
Oh, interesting.
Yes, a company can build an on-premise private cloud in their own basement. But the modern solution is a hosted private cloud. The CTO can go to a major cloud service provider and lease dedicated physical servers within the provider's data center.
So she is renting the hardware, but she is the only tenant allowed on that specific hardware.
Precisely. No other company's data will ever touch those specific silicon chips. The hardware cost remains an operational lease expense, avoiding the massive capital outlay.
But the bank's IT team maintains exclusive, granular control over the hypervisor, the security policies, and the physical isolation of the data.
It perfectly bridges the gap between cloud economics and the stringent security demands of a private environment.
Building the right container for the data your business model generates. We have covered an immense amount of ground today. Let's step back for a strategic closing and recap the primary managerial takeaway of this entire deep dive.
It's a lot to synthesize.
It is. The transition from legacy analog signals to complex XaaS cloud environments, governed by an almost infinite IPv6 addressing scheme, is not just a routine IT upgrade. It is a fundamental shift in how an enterprise exists.
It dictates everything.
It dictates how a business communicates internally using unified communications and business process management. And it dictates how it competes globally across B2B and B2C markets. To tie this explicitly back to our opening discussion, mastering this infrastructure, intentionally designing a network that filters, prioritizes, and automates the flow of data, is exactly how a manager conquers the information overload of the hyper-connected world.
You have to build a strategic brain for the corporate nervous system.
Exactly.
That synthesis is exactly what corporate leaders need to internalize. And it sets up the next piece of the puzzle perfectly. I want to offer a high-level strategic tease for our upcoming chapter. Chapter 2 is titled, Solving Today's Business Communication Challenges. Now that we understand the baseline technology, the mechanisms of IP packets, the cloud service models, the UC platforms, we have to learn how to actively wield them as architects.
Okay.
We are going to explore how managers take abstract, messy communication requirements from their business units and transform them into strict, deployable network specifications. When the marketing department says, we need faster video streaming, how does IT translate that into actual routing protocols and hardware purchases? That is the translation challenge we tackle next.
That is going to be incredibly practical. As we wrap up Chapter 1, I want to invite you to take a second to like, subscribe, and share this series. Subscribing ensures you always maintain a competitive edge in the hyper-connected marketplace as we continue to break down these critical enterprise strategies.
It really is a must.
Please explicitly check out the description below for access to additional corporate resources, diagrams, and technical reading that pair perfectly with the concepts we explore today. Also, take a moment to review the channel for other corporate IT playlists, video modules, and deep dives designed for continuous professional education.
Lots of good stuff there.
We highly recommend checking out the Digital Forensics podcast series and the Network and Systems Security podcast series hosted on the channel. They provide fantastic, specialized context for the infrastructure discussions we are having here.
Before we sign off, I want to leave you with a reflective, high-impact question to mull over. As IoT autonomy continues to grow, removing humans from the loop entirely, and as our networks move completely to the abstract cloud, will our business processes ultimately dictate our network architecture, or will the immense capabilities of the network architecture begin to dictate how we design our business processes?
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.